Okay, this is our first example in section 4.5, applied optimization problems. So here we go. We start with reading the problem. Times are tough and the budget is tight. A farmer has a strict $4,800 budget for fencing a field. The fencing running east to west requires extra bracing against the wind and costs $12 per meter. North-south fencing only costs $8 per meter. Help the farmer find the area of the largest field they can fence. Okay, so here we go. Let's take a look at our solution steps up here and start with step 1. We're going to make a sketch and label it and introduce our variables. So we need to draw a field here that is fenced in, and keep in mind your little compass directions, north, east, south, west. There we go. And we can pretty safely assume that since it's talking about east-west and north-south fencing, that we've got a rectangular field set up here. Okay, something with fencing running north and south and then fencing running east and west. All right, so I'm going to label the variables here. And just generically, I'm going to call this L for length and this W for width. You could choose different variables if you want. It doesn't really matter. You could call it W and H or even X and Y if you really felt like it. You just need to come up with some sort of variable that makes sense to you. Okay, and then I'm going to label a little bit of the information on here just to help me remember what goes where, because we can see there's two different costs for this fencing. The fencing running east to west costs $12 per meter. So that would be in this horizontal direction here. So on side W here, that costs $12 per meter. Okay, and then our north-south fencing along this vertical direction, that only costs $8 per meter. So let's note that as well. Okay, because there's some wind coming along here, probably blowing up against the east-west directions. So that fencing needs a little extra reinforcement and it costs more. All right. Now, let's see, we have made a sketch, we've labeled it, we've introduced our variables, L and W in this case, and now let's identify our goal. Are we trying to maximize something or minimize something? And what is that thing that we're trying to maximize or minimize? So you pick through the problem here, and we are trying to help the farmer find the area of the largest field that they can fence. And so those circled words are key ones to look out for. Our quantity is area, and we want the largest. So our goal is going to be to maximize the area. So goal, maximize area. Okay. Now, step 3, form an equation or a function for our variable of interest. Okay. I'm going to just say area will be represented with the variable A. And so our equation here is going to be the area equation for this rectangle. A equals LW. Ta-da! All right. Now, step 4, use the given or extra information to make this into a function of only one variable. Because remember, if we're going to be looking for critical points, trying to find a maximum in this problem, we're going to need to take the derivative of our function at some point. And right now, when L and W are both involved, we can't really get a nice first derivative to work with on that. So we need to incorporate our extra information. And if you'll look at this, what information we haven't used yet would be our budget information. Our farmer has a strict $4,800 budget, and we've got this pricing information for the different types of fence. Okay, so that we would identify as our given information. This is also sometimes called a constraint. Okay, it's something that has to be met in this problem. It's an extra criteria for the solution here. The solution of this problem needs to maximize the area while still adhering to this constraint of the strict $4,800 budget. So this is going to be our budget / cost information. All right. And so we would say that the farmer's total budget, $4,800, would need to add up to the sum of the price for all this fencing. So we have two sides here that are $12 per meter, right there and right there. Okay, each one of those is W meters long. So we would have the $12 times two of those W sides. Okay, so that would be the total cost for the kind of green outlined fencing there, all of the east-west fencing. And then we would need to add on the cost for the north-south fencing, going this direction. Okay, that's the cheaper one at $8 per meter. And we have two sides of length L there. So you'd have $8 per meter times a total of 2L meters. Okay, 1L on each side there. So there's our north-south fencing. I guess I could label that for you guys who are looking at these notes on Canvas later. So east to west there, and then this is the north-south fencing. And it all has to add up to the total budget of $4,800. Okay, so we have an equation there. This is our constraint equation. 4,800 equals 24W plus 16L. And what we're going to want to do here is solve for one variable or the other, solve for either L or W, so that we can take that and plug it back into our area equation here to get that all in terms of one variable or the other. So you can really choose whichever variable you want. You can solve this for L or W, doesn't really matter, and there's not a huge advantage to one or the other. So I think I'll just solve for L, sure. Okay, so let's see, 16L would be 4,800 minus 24W, and we could reduce that a little bit. We could say all of those are divisible by 8, so 2L equals 600 minus 3W. And then divide everything by 2. And L is going to equal 300 minus 3 halves W. Okay. So we've solved for L in terms of W, and now we're going to put that into our area equation. So we're going to bring these two things together here. Okay, so area is going to be L times W, I guess I could write that up above a little bit. A equals LW. And so when we substitute in what we just found for L, that would be 300 minus 3/2 W. Okay, that is L, and then times W. Okay, and so we're going to come up with a nice equation for the area here, and it's all in terms of the variable W. So just in terms of one single variable. Okay, so let's bring that down here and boop, write our area equation in terms of W alone. I'm going to go ahead and distribute W in there. That's going to help us with our derivative that we're going to need here real quick. That's 300W minus 3/2 W squared for the original equation there. And now we are going to take the derivative. Okay, we've done step 4 here. We've made our area function into a function of only one variable, a function of W alone now. And so, yeah, now for step 5, our goal is to find the maximum or minimum value. We need to test our critical points and domain endpoints if applicable. So for critical points, we'll need our derivative. Domain endpoints, let's see. Well, we would want L and W, I'd say, to be greater than 0. Since they are fence lengths, you would want to have some fence there, yes. And then there would be some degree of a constraint on this. You couldn't consume your entire budget with just east-west fencing or just north-south fencing. So the domain endpoints, I don't think they're going to be a huge deal here. We can go with just our critical points, it looks like, because the endpoints of that would be, yeah, either consuming the entire thing with east-west fencing, which would leave no room for the north-south direction, and that's not good. Or if you consume the entire budget with north-south fencing, then you don't have anything east to west, and that's not really good either. So, all right, so yeah, our domain endpoints don't really particularly apply there. Wouldn't make too much sense anyway. So yeah, let's find our derivative, A prime, or dA dW in this case. So that would be 300 minus 3W. Nice. And now for our critical points. We would want to see, okay, A prime is never undefined, so that one is good. And so we would want to set A prime equal to 0. 300 minus 3W equals 0. So that would be 3W equals 300, giving us a W value of 100 for our critical point. Okay. And just to make sure that that is truly going to give us what we want, let's test real quick here. Our derivative, A prime, put our critical point of 100 on there. And our derivative equals 0 right there. That's nice. Okay. If you pick some number that is less than 100, all right, like 0 or something like that, you would see that you would get a positive value for the first derivative there. So our first derivative is positive here. And then if you pick a number that is greater than 100, you could go wild, pick 1,000, whatever. If you plug in any number that's greater than 100, you're going to get a negative value for your first derivative on account of that second term there. So we can see that our derivative switches from negative to positive, or sorry, other way around there. positive to negative. It switches from increasing to decreasing. Okay, so increasing to decreasing, that tells us that there truly is a local maximum value for area at W equals 100. So this is a max value. Check. That's a good little check to run on your derivative there. So we are really getting a maximum value for the area, which is what we wanted to do. That's great. Okay, so for our solution here, we have W equals 100 meters. And then L equals, oh, there's our expression for L right there, 300 minus 3 halves W. Okay, 300 minus 3 halves W. So that would be 300 minus 3 halves times 100. So that right there is 150. And so that would leave us with 150 meters for L. And so those are our dimensions. And just to double check here, they wanted us to find the area of this largest field. So not just finding the length and width, but actually compute the area measurements. So A equals LW, 150 meters times 100 meters equals 15000, 15,000 meters squared. Okay, this is the area of the largest field. All right. And then just to make sure that that makes some amount of sense, the sign of that is positive. Good. We want positive area. The units make sense. Square meters is an area measurement. And the magnitude of this, 15,000, is large, yes, but this is a farmer's agricultural field that we're talking about. And the length and width there seem, pretty reasonable. 100 meters is about, football field length. So yeah, this is not like a tiny little, garden patch or something. And this is also not the size of Kansas or something like that. So this seems approximately on the right scale for an answer. Okay, so there is our first optimization problem. We maximized the area of this field given the constraint of the budget.